Hi guys, welcome to Netgate Chemistry. So in this video we are going to continue with the topic of stereoisomerism in octahedral complexes. So the first type of complex in this particular video which we are going to study is Ml2A2B2. Now in this case we have these two ligands of same type, these two ligands of same type and these two ligands of same type. So what first I'm going to do is I'm going to provide these three type of ligands all having cis positions. So how I can do that? First I'll place these two ligands, then these two, and then these two. All of them are cis with each other. Now if I look for the plane of symmetry, then you will realize that there is no plane of symmetry here. So because there is no plane of symmetry, so the compound is going to be optically active. So there will be one enantiomeric pair present. Now this is first case when I have tried to make all the cis positions possible. Now secondly I will try to make two pairs having cis positions. So what I'm going to do is I'm going to provide two pairs the cis positions and one pair for transposition. So first I'll place the pair having transposition. So suppose B is getting transposition. So A is getting cis position like this and L is getting cis position like this. Now if I look for plane of symmetry, so plane of symmetry is present. So compound is optically inactive, having no enantiomeric pairs. Now here in this case I can play around with the ligands. Suppose first case I have given transposition to these two B ligands. In the second case I can provide transposition to the A ligands like this, and B will be cis, L will be cis. Also I can give transposition to these two L, and here A will be cis and B will be cis to each other. So here we have three enantiomers. Now here I have tried to give two pairs cis position and third pair transposition. Now I'm trying to give two pairs transposition. So what you will observe is that when I'm going to give the two pairs transposition, so the third pair itself is going to get the transposition. There is no case of two pairs having cis and two pairs having trans and one pair having cis position. So when two pairs get transposition, the third one is also going to get the third pair is also going to get the transposition by default. So if I'm giving transposition to these two L and transposition to these two A, so remaining two positions are transpositions. So B will be getting the transposition by default. So by default these three will be getting the transposition. So this is the third case in which I have tried to give two pairs transposition and the third was occupying transposition by itself. So here also we are having plane of symmetry where these two L will be reflecting each other. So plane of symmetry is present, compound is optically inactive. So far for the case of Ml2A2B2 we have these pairs possible, these stereoisomers possible. So with this we'll move on to the next case. Now the next case which we are going to discuss is Ml2A2BC. Now this case you can do it as a homework. cases will be similar, cases formed will be similar. First you will try to form all cis, then two pairs having cis, one pair having trans, then at the end you will try to form two pairs having trans, then by default third pair will be having the trans position. So this way you can do the stereoisomers for these compounds as well. So now with this we'll move on to the third category. So third category will be for ML3ABC. Here we have three same ligands. So whenever we are going to have three same ligands, they will be forming Fak and Mer isomers, right? And here we are having three different isomers. We'll look for it how they are going to give us different forms of stereoisomers. So first we are going to form Fak and Mer. Why? Because we have three similar ligands, so they are going to form Fak and Mer isomers. So first we'll form the Fak isomer. So for Fak isomer, what we are going to do is we will be having these three positions, right? Actually they form a triangular face, that is why they're called facial. So this way these three ligands, okay, instead of A we are having L, so here we are having 3L. So this is the facial arrangement in which we orient these three same ligands like this so that they can form a triangular face. So we have discussed it earlier also. So this way we'll place these three and remaining A, B and C will be occupied here, right? If we look for plane of symmetry, then plane of symmetry will not be present in this case, so the compound is going to be optically active, right? This is about the Fak isomer. Now if we look for the Mer isomer, that is meridional. So what is going to happen in that case? We have to give, we know that two ligands should be at 180 degree angle. So these two ligands will be at 180 degree angle with each other, and third will be at 90 degree with these two ligands. So this is the orientation for Mer isomer. So remaining three positions will be occupied by A, B and C. So this will be the Mer isomer. Now here what you can observe is that you are having plane of symmetry, right? This L will be reflecting this L. So plane of symmetry is present, compound is optically active, so it will be having one enantiomeric pair, right? Enantiomeric pair is nothing but the mirror image of it. Now what we have to look for is, here we have A, B, C, three different ligands. Now there will be a role of these three ligands. What you are going to do is, first you are going to place A and B opposite to each other, then A and C, and then B and C. By exchanging the positions you will be getting different enantiomers, just like this. In this case we are having A opposite to C, so this one is done. Now we have to first place B opposite to A, and then we have to place C opposite to B opposite to C. So what we are going to do is, these three positions are fixed. First I'll place A and B opposite to each other, A and B opposite to each other, this will be C. Then I'll place B and C opposite to each other, and here will be A. So these are the two more isomers which are present. So there are total four geometrical isomers possible in this case, right? 1, 2, 3 and 4. There are four geometrical isomers total for ML3ABC. Now with this we will move on to the next category. Now the next category which we are going to discuss is of the ML3A2B. Now in this case, here first you will observe that there are three similar ligands, so they will be giving Fak and Mer isomers. Now we also have two similar ligands, so they will be giving cis and trans isomers, right? So first we will go for the Fak isomers. So first we'll make facial. How? For facial, these three positions will be occupied so that they can form a triangular face. For remaining two positions, first I'll place these two A adjacent to each other like this, A and A. Here will be the B, right? Now this is the Fak isomer. Now what you can observe is that here in this case you cannot play around with the ligands to form cis and trans isomers because there are these three positions, and anyway by interchanging these ligands you cannot form cis and trans isomers. So in this case cis and trans is not possible. Now if we look for plane of symmetry, then can you find plane of symmetry? No. So there is no plane of symmetry, so compound is optically active. Now if we look for mer isomer, then in mer isomer, first what we will do, we will assign the positions. First we will place two ligands at 180 degree and third ligand at 90 degree with these two. Now we have these three positions. First what I am going to do is I am going to place 2A adjacent to each other like this and B here, right? This is the first case. Now what I am going to do is I am going to make similar arrangement for L. Now instead of giving these two A adjacent position, I am going to place them at 180 degree angle with each other, that is opposite to each other, and B will be here. So here what you can observe is this is cis and this is trans, right? This is cis and trans. If you look for plane of symmetry, then definitely plane of symmetry is present in both of these cases, right? So as you know, plane of symmetry is present here, so the compound is going to be optically inactive, right? So basically these two are optically inactive, whereas this one is optically active, right? So this is about ML3A2B, right? Because of these three L, same L, we have Fak and mer, and because of these two similar ligands we have cis and trans within meridional isomer, right? Now we will go for the next category of compounds, that is ML4AB. Now in this case what happens, we have four ligands same, so we will place four ligands here and two ligands A and B here, right? Now what you can observe is that if we look for plane of symmetry, then we can pass a plane through these four ligands and these two L will be reflecting each other, right? If you're not able to imagine this way, what you can do is you can simply, because these six positions are equivalent, what you can do is you can give these 4L these positions and A and B at 180 degrees, just like this, right? We have just rotated it by 90 degrees, nothing else we have done, right? So if you rotate by 90 degrees, you will be getting orientation like this, although these two orientations are same actually, but just for understanding we have done this, we have just rotated this by 90 degrees. So now if we look for plane of symmetry, now you can see these two ligands will be reflecting each other, right? So plane of symmetry is present, so compound is optically inactive. Now what you can observe in this case, we are having A and B here and here, right, opposite to each other. What else can happen? These two ligands can occupy adjacent positions to each other also, like this, A and B adjacent to each other, right? So this will be the cis position. This is the trans positions, because these are sort of transposition, we can say, because they are opposite. So these are sort of transpositions, sort of, and these are sort of cis positions, not exactly cis, but we can say sort of a cis position. Now if we look for plane of symmetry, again this will be the plane, right, and these two ligands will be reflecting. Again, if you have problem in imagining this, what you can do is you can again rotate this by 90 degree, and what you will be getting is A here, B here, these ligands here. Now you can see the plane of symmetry, and these two ligands will be reflecting each other. So here also plane of symmetry is present, so compound is optically inactive. So till now we have discussed so many cases. There is one more case left, that is of M, and all the ligands are different. All the ligands attached with metal is different, that is A, B, C, D, E, F. All the ligands are different. So what you can do is you can look for the orientation, different orientations. How? You can first place these two opposite to each other, then these, this one, and then this one. Similarly go for B like this, right? Similarly you can go for C like this, for D also and E also, right? So this way you can find out total number of isomers possible for this one also. So this is very easy now, so I'm not going into the detail of it. So this way you can find out the total number of possible isomers in this case also. So using this concept you can find out the total number of isomers present, and total number of isomers will come out to be 30, because this way you will be having 15 possible orientation, right? These kind of orientations will be 15. You can solve them by your own, and because you will be having enantiomeric pair also, so each one will be having in pairs, so that way you will be having total 30 isomers, because each of the stereoisomer which you are forming, right, using this way, each one will be having one more enantiomeric pair, so that way you will be having total of 30 isomers, right? Now there is one more thing to discuss, that is in case of coordination number 6, when you are having bidentate ligands like these types. So what you are going to do is you are going to look for the plane of symmetry. So in that case, how you are going to look for plane of symmetry, I am just going to show one or two examples, and then you will be able to solve all sort of coordination number 6 complexes having bidentate ligands. So it can be like this. If you are having metal with this sort of a ligand, so it will be placed like this. So what happens, because of this ring we cannot divide this ring into equal parts in any way. No matter how you are going to place your plane of symmetry, that plane of symmetry will never be present. So this thing you have to keep in mind while you are making the plane of symmetry in case of these complexes. So this thing you are going to keep in mind while you are while you're looking for plane of symmetry in coordination number 6 complexes which are having the bidentate ligands. So what I'm going to do is before starting with the Jahn-Taylor distortion in the octahedral complexes, I will be providing you with the full table. Meanwhile, what you can do is you can try out all the coordination 6 complexes having bidentate ligands and find out the number of enantiomers, right, optical and all the stereoisomers in case of coordination number 6 complexes. So I will be discussing after 1 or 2 videos, and I'll be giving you whole table in which I will be mentioning how many isomers will be present in each case, but you have to solve that by your own, right? So that way you will be having some practice also. So after 1 or 2 lectures I will be providing you with that table as well before starting with Jahn-Taylor distortion in octahedral complexes. So far that's it for this video. Thank you so much for watching.